Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, here we go with our next lesson. This is 1.2.1, Introduction to Probability. All right, so before we get started on the lesson, a couple of terms. I want you to understand the difference between probability and chance, and there really isn't much difference at all. So when we're thinking about probability, probability is the likelihood that an event will occur, and it is expressed as a fraction or a ratio. So examples of that would be like, what are the chances that when you flip a coin, you are going to flip a heads? Well, there are two sides of the coin, and only one of them is heads. So that would be expressed as a 1/2 probability, 1 out of 2, basically. I think you want to think about it as a ratio. Nah, I don't think that. Just write it as a fraction. Okay. So what does that mean for chance? How is chance different than probability? Well, it really isn't, with the exception of how you represent it. So chance is the likelihood that an event will occur, expressed as a percent, not as a fraction. And so, you might say you got a 50-50 chance or a 50% chance of flipping a head when you're flipping a coin, because 1 out of 2, 1/2 is the same as 50%. So a lot of times we'll use the word chance when we're talking about probability, and we almost always express it as a percent. Like, what's the chance it's going to rain tomorrow? Oh, only a 10% chance of rain in the forecast. So they both mean the exact same thing. And I'll tell you right now, this math program sometimes goes back and forth between them, and that's totally okay. You can say that the 50% chance it's going to rain is a probability. It's not like it's horribly wrong if you express either one of those with a fraction or a percent. But typically, the probability is given as a fraction, chance given as a percent. Right, so you probably heard a weather forecaster say that the chance of rain tomorrow is 40%. Have you thought about what that means? Does it mean that it will rain tomorrow for sure? What is the chance it will not rain? In today's lesson, you will investigate the chance or probability of something happening or not happening. As you do the activities, ask your team these questions or think about these sorts of questions as you're working through it. What's the probability that an event will occur, and how do we record that probability? Okay, so first things we would do is you would do this in your team, but you can kind of think of this on your own, give you a chance to pause the video and write down a couple of ideas that you might have. The directions say make lists of 3 different types of events. One event is possible but not certain to happen. One event would be certain to happen, and another event, and these are things that could be like in real life, that would be impossible to happen. Okay, so pause the video, see if you can come up with one of each. You can come up with multiple of each one if you want. Like, if you can only think of one that's certain, but a couple that are positive and one that's impossible, that's great. Do more than one each if you feel like it. Otherwise, just try and come up with one of each. Okay, so I came up with a couple of ideas myself. So what we're going to do is I'll show you, I've got them down below here. I'll show you what my 3 are, and then what we want to do is we're going to draw a line segment, and we're going to create a likelihood scale. And this is what the likelihood scale is going to look like. It's going to be like this. Now you can have a scale that has 3 parts to it, where it has just the 0 on one side, the 1 on the far extreme side, and then halfway point. I added a 1/4 point and a 3/4 point, just to give us a little bit more flexibility with that. It's possible to happen, but not certain to happen kind of likelihood or probability. So looking over here, you see I wrote down 3 different items. Rain in the forecast. Could it rain? Is it impossible to rain? Or is it absolutely certain to rain? typically, like on some days, you might say it's impossible or certain, but for the most part, that's going to fall somewhere in that, possible, but not certain or impossible. Okay, so what's the likelihood of rain? Is it 50%? Is it 40%? Is it 25%? Is it 75% chance of rain? This is going to fall somewhere in the middle. And the full moon this month, there's always a full moon. It's not always a full moon. Every month, the moon goes through phases, and at some point is going to be a full moon. So we're going to put that in the 100% certain that at some point this month, there is going to be a full moon, and I wish I would have written that a little bit differently, but here, maybe I could do this. No, that's terrible. We'll just leave it like that. You know that's going toward the old 100%. And then the sun will rise in the west. No, that doesn't happen. The sun rises in the east. If the sun starts rising in the west, then we're facing Armageddon, and all life as we know it will cease to exist. So we won't even care. Yeah, that's impossible. So where do the anything that is possible but not certain, where does that fall in our likelihood spectrum here? It's hard to tell. But that's what we're going to be dealing with here is, for the most part, we're going to look at some different situations that are possible, a few that are impossible, some that are certain, but mostly possible but not certain, and figure out what is the likelihood or the probability or the chance of those things happening. So here we go. This is called Go Fish. To win a giant stuffed animal, Mike needs to catch a green fish. If all the fish in the tank are green, how would you describe the probability of Mike's winning a giant stuffed animal? Don't look at this down here. I'm going to put a little shield up here for a second. And I'm going to change my shield because I don't like that color. Where are you? Where's the color? Ooh, I like that one. So, all right. So if all the fish are green, can you get any other color besides green? No, you can't. So doesn't that mean that this is 100% certain that you're going to get that giant stuffed animal? Not much of a contest if you have to get a green fish to win, and that's all they have are green fishes. Why don't they just give out the stuffed animal? I don't know. I'm digressing a little bit. At any rate, that would be a situation where you would have 100% certainty of picking a green, therefore getting the giant stuffed animal. The way the tank is set up, you've got 1 green, 3 blue, and 6 yellow fish. So that's where we've got this set up down here. What are the chances of getting a blackfish? Well, do you see any blackfish there? No, you don't. So that means we're talking about 0% chance. That is impossible to get a blackfish. So given the information in this problem, what percent chance, or what percent of the time would you expect Mike to catch a green fish and win the giant stuffed animal? Okay, so this is a practical application of probability. How many green are there? There's only 1, correct? So that would be 1 out of the 10 fish are green. And so can we translate that into a percent? What is 1/10 the same as? If you said 10%, then you are correct. If this is the current setup of the fish tank, and Mike can only win the giant stuffed animal if he catches a green fish, then you expect 1 out of every time he tries to get a fish, 1 of those would be green, so that would be 10% of the time. So Mike has a 10% chance of winning a giant stuffed animal on any given draw. Is that what we're doing? Are we drawing the green fish out? I'm not quite sure what we're doing. Are we hooking them? Are we just grabbing them, catching them? Okay, whatever. Let's move on. Okay, so let's talk about how we find probability. The first term I want you to write down in your journal is desired outcomes. The desired outcomes are the outcomes that you're looking for or want to happen. So when you were searching for the green fish was the desired outcome, right? When you were looking for the blackfish was the desired outcome. If I'm going too quickly, I know this is probably intuitive to you, but I'll say it anyway. Just pause the video, copy everything down, and then back it up a couple seconds, and then replay it, and you'll get everything. Possible outcomes, well, those are all that possibly happen. So if we go back to the fish scenario, there were 10 possible fish to pull out, right? 6 of the yellow, 3 of the blue, and 1 of the green. So that would be 10 possible outcomes here. And which brings us to our formula for theoretical probability. The theoretical probability is written as a ratio. It is equal to the number of desired outcomes over the possible outcomes. And so that's what we had here. And there's this symbol that we use for the probability. It's like a capital P written sort of like an italic P. And you have your desired over the possible, which sometimes we'll call the total, okay? So in the case of the green fish, there was only 1 green fish out of a total of 10, and that's how we got the probability of 1/10, which we converted to 10% chance, okay? So this you want to have written down. This is extremely important. We'll be using this throughout the year anytime we talk about any type of probability. The total always goes on the bottom, okay? It's always, your probability is always based on the total, and the base is always on the bottom, right? You think the base of a lamp or the base of a tree are always at the bottom of the tree. The base, it's always based on the total, that always goes on the bottom. All right, so with that in mind, I want you to answer these questions. Pause the video if you need to. Here's all the fish in the tank. Here are the numbers. 1 of them is green, 3 are blue, 6 are yellow. There's a total of 10. So with that in mind, you need to identify what would be the probability of pulling out a blue fish and what would be the probability of pulling out a yellow fish. Write them as a fraction and a percent, okay? Make sure that you label everything properly. And then after you've completed that, then what is the theoretical probability of getting a fish that is green, blue, or yellow? And I corrected this. That is a fish that is any of those 3 colors. How would you write that as a probability? How would you figure out the probability of that? Okay. So pause the video, go ahead and write down what you think are the correct answers for A and B, and then I'll share with you the answers that I have. Alrighty, so what do we have here? For the blue fish, there were 3 blue fish, so 3 out of 10 is the same as 30%. So Mike has a 30% chance of catching a blue fish, or a 3/10 probability. Yellow, how many yellows are there? 6 out of the 10 fish are yellow, so the probability is 60%, or I'm sorry, the probability is 6 out of 10. And the percent is 60% chance of getting a yellow fish. So what do we do here? The probability of getting a green, blue, or yellow. So I like to think of probability as like winners and losers. In this case, anything that wasn't blue was a loser. There were only 3 winners there, right? Anything here for the yellow that wasn't yellow was a loser. So the 6 fish are the winners. Well, if you're a winner by getting either a green or a blue or a yellow, doesn't that make every single one of those 10 out of 10 winners? So when we've got probability where we are saying you can either get this or that, that increases your chances of being a winner, correct? So you add your desired outcomes together. You add the probabilities together anytime we are finding the compound probabilities that involve the word or. Later in the year, we'll talk about what you're supposed to do when you have probabilities where you have to get this and that. So the word or versus the word and implies doing a different type of operation, and we'll talk about that thoroughly when we get to that point. So you got 1, 3, and 6 make a total of 10 out of 10, which is 100% chance, which means it would be certain that you would get one of those 3 colored fish, because that's all that's in the tank. All right, so now let's take a look at this spinner. This spinner has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total wedges, all equally sized. That's really important. That means the probability of landing in any one of those 10 is the same. It's all a 1/10 chance. My dog is barking. If you don't mind, I'm going to pause the video for a second, go let him in, and then I'll continue with this. All right, Bubba's been taken care of. Where did I leave off? 10 equal parts. That's really important because you want to have all those be equally likely. Of those, it looks like there's 1 yellow, 2 green, 3 blue, and 4 red. All right, so I would really like for you to pause this video now and copy this spinner down. You don't necessarily have to color those in, but you can put a G here and an R there and a Y there, or if you like to be artistic, go ahead and color those in. Make sure that there's 10 equal parts, or at least looks like it. And then, you know, it really is a good idea for you to copy down these questions. I don't think anyone really wants to do that, so I'll let you decide if you want to do that. So pause it and do all that work if you want to, but for sure draw the spinner. I want you to do that. But I'm going to move on, and you can pause and catch up in a second. So which color is the most likely result of the spin, and how do you know? Well, the one that's the most should be the one that you have the highest likelihood of spinning and landing on, right? So wouldn't that be the red? There's more red than any other color, right? And which one is the least likely to happen? Well, which one only has one? Yellow would be the least likely one to happen because there's only one yellow and there's more than one of every other color. So here it says work with your team to determine the theoretical probability of the spinner landing on each of those 4 colors. You don't have your team, but let's just think about, once again, how many total wedges are there, how many different sections. There's a total of 10. Those are your possible outcomes. And how many of them are red, how many are green, how many are blue, and how many are yellow. Write down those probabilities as fractions, and then again as percents. While you're doing that, I'll talk to you about these last couple, and then I'll reveal these at the end. What's the probability that the spinner is going to land on a purple? Well, there are no purple. And don't give me that story about landing between the blue and the red is going to be purple because they're going to blend together to make a, what is that, a tertiary, secondary color? Yeah, that's a secondary. No purples. So it's going to be impossible. And then what's the probability of landing on either a red or a blue? Okay, well, let's go do these, reveal these 4, and then we'll come back to E. So what was the probability of landing on red? There were 4 out of 10, so that was 40%, correct? What's the probability of landing on green? There were 2 out of 10, so that would be 20% chance. Blue had 3 out of 10, so that would be a 30% chance, and the yellow was 1 out of 10, so that would be 10%. So let's say that you want to land on either red or blue. That makes both of these winners. So how many total winners are there? Well, there's a winner, 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 and there's a winner. So you got a total of 7 winners, correct? So when we add 4 plus 3, we get 7, and therefore the number of desired outcomes are 7. So that's a 7/10 probability of landing on either red or blue, or a 70% chance of landing on either red or blue. Okay, now we're going to go into the realm of experimental probability. We've been working with theoretical probability because we know the total number of parts and we know the number of desired outcomes, and so we can always write the theoretical probability using that those ratios. But sometimes you don't know what the actual probability formula is. Things can get pretty complex. Like, for instance, what's the probability of winning the lotto? How do you even figure that out? Mathematicians and statisticians, they know how to figure those things out, but it's really complex. Later on, we're going to have a lesson where we work with computer simulations to try and figure out the probabilities. But sometimes when you can't figure it out using the pure mathematical formulas, you're just not quite sure what to do, you've got an alternative. And that alternative is conduct an experiment and see what you get from your experiment. So the experimental probability is the probability of an event occurring. Stop it. What's going on here? based on or derived from conducting a trial or, oh no, it's not a tally, it's a tally. Hold on for a second, can't have that. Tally the results. Okay, so what we're going to do here is we're going to spin this spinner 10 times, and we're going to record the number of times that we get red, the number of times we get green, blue, and yellow. And we'll see if they actually match the theoretical probability of the spinner that we had here. Okay, same spinner, right? 4, 3, 2, and 1. Yeah, same spinner. All right, so let's do this. You write down the 4 colors, and you keep track as I do this. So here's the first spin. It was a blue. A little check mark there. Second, oh, stop it. Second spin. Green. Third spin. Red. Fourth spin. Red. How many times do we expect the red to come up in 10 spins? Something to think about there. Green comes up again. I expect the green to come up anymore. I've already got 2 times. I haven't split it 10 times, but the probability was 2 out of 10, so I don't expect the green to come up anymore. Does that mean it won't come up anymore? No, not necessarily. It could. Came very close. That was a blue. And a red. How many is that? 3, 4, 5, 6, 7. I got 3 more to go. At some point, I'm expecting a yellow to come up at least once. But it maybe not. There's the green. That's 1 more green than we expected. We only expected 2 to show up. And there's another green, so that's 4. And then the last one, right? This is 6, 7, 8, 9. One last one. See if the yellow ever comes up. And it didn't. Holy moly. All right. So if we only did this experiment 10 times, and these were our results, you would think 5 out of 10 times green showed up, so half of the spinner must be covered in green little wedges, but that's not the case. Let's do it another. How much time do we have? Ooh, we're getting late there. All right, if I do it 20 times, let's see if it gets closer to our ratios. All right, I'm going to do this really quickly. You keep track. There's blue. Blue. Stop it. Why are you there? I want you there. Oh, well, whatever. Let's do it again. We got another blue. There's our yellow. Yellow did not get shut out. Red. Red again. So what is that? 15, 16. I got 4 more to go. Red again. We had blue. We got red again. I think that's 1 more I need. This is 5, 10, 15, 16, 17, 18, 19. This will be the 20th roll, or spin. And we got blue. All right. So, oh, I should have recorded how many I got the first time. Either way. All right. Right now, our red is equal to 7 out of 20, which is the same as 35%. Green is equal to 5 out of 20, which is, I believe that is 25%. The blue was 1, 2, 3, that's 7 out of 20, which is 35%. And the yellow was only 1 out of 20, that's a 20, which is equal to 5%. Okay, so the green started off at 50% and then went down to 25%. The actual percent should have been 20%. So by going 20 times instead of 10 times, it's got closer to its actual probability or percent. The yellow was at 0, and then, or was it? No, yeah, it was at 0 and it moved up to 5%, which is closer to the 10%. And the red and the blue got closer. So what we find is this. The question, will the experimental probability always match the theoretical probability? The answer is no. However, the more trials that you do, the more times you conduct your experiment, the closer the probability is going to get, the experimental probability is going to get to the actual theoretical probability. Okay? So what people do is, when you're not quite sure what the model is, you're not quite sure how to find the probability, but you know how to conduct an experiment, you can run this simulation 10, 20, 100, 1,000, a million times. If you've got a computer that you can just have it go at it and just keep a tally of everything, the computer can do it in a split second. After a million times, your percents are going to work out pretty much exactly what the theoretical probability is. And so that's a lot of times how people figure out theoretical probability, by running simulations and doing experimental probability. So I think that's it for today. That is good job. Look on your homework, and we'll be exploring probability even more in the future. Bye-bye.
Hey, feeling good, like I should. When in dark, walk